Okay, we're back for the second video in this lesson. So it's the second video in 6.08. We just calculated the equation for our best fit line. Y equals 2/3 x minus 6.2. It's the best fit line for this data from the Great Wolf Lodge Water Park. And what we're doing here is we're going to talk about our predicted attendance and our error. Now, what we've done is we've come up with an equation to draw this best fit line. And the best fit line approximates what the data was telling us, okay? Now what we're going to do is we're going to use this equation and see what would this equation give us as an attendance for these temperatures. And we're going to call that the predicted attendance. If I take 62 degrees and I put it into this equation, what would I predict the attendance to be? You can trust me, or you can pause the video and check my calculations. But if I take 62, put it into that equation, I get about 35.1. So the equation tells me that when it's 62 degrees, I could expect about 35,100 people. I'm going to go ahead and fill that column in. I'm just taking the x values, plugging it into the equation, and getting these. Okay, so trust me, or you can, pause the video and do it yourself. This is 38.4, 39.8, 40.4, 41.8, 45.1, 46.4, 47.1, 49.1, 50.4, 52.5, 56.4, 57.8, and lastly 59.1. And you can see that the predicted values of attendance are pretty close. They track along pretty good with the actual attendance that was measured. Okay, now let's start talking about error. Remember, this line that we drew only went through a fixed point here at the balance point. And I could have adjusted this line a little bit this way or a little bit that way. Okay, there is an actual best fit line. And if I get time, I'll show you how to actually calculate that with a calculator. But what we want to do is we want to say, well, how can we make adjustments to this best fit line to make it even better? What we have to do is calculate the error. Now, error comes in when you start measuring how far these actual points are from the line. Okay, so it has to do with the distance that these points are off your best fit line. And you want these distances to balance out. Now, in an ideal world, these dots would be exactly on that line and there would be no error, right? So to calculate error, we take the actual attendance and we subtract the predicted attendance, and that gives us an error. So if I were to take 36.8 and subtract 35.1, it would give me 1.7. So that point has an error of 1.7. What we're going to do is we're going to do all those calculations. I've done them ahead of time, but again, if you don't trust me, pause the video, you can fill it in. We've got 2.5. So that's telling me both of the actual points were above the line. But watch what happens now. If I take 36.9 and subtract 39.8, I get negative 2.9. And we'll just go on. Negative 3.3, 2.5, negative 2.8, negative 0.6, negative 1.7, negative 0.7, 1.1, 5.2, 0.9, negative 1.7, and negative 0.2. So that's the error. Now, what we want to do is we want to have the summation of these errors get as close to zero as possible. And as we make adjustments to this line, we can make that summation of these errors approach zero. It's not going to get to zero because look, my points aren't on the line. So we can't get to zero, but we can make it smaller. We're actually going to tackle that in the next lesson, what to do with those errors. So that concludes the lesson. We took bivariate data. It's called bivariate data because bi, like bicycle, has two wheels. Variate, variable, so two variable data. We plotted them, found a balance point. Through the balance point, we drew our best fit line. For the best fit line, we came up with an equation. We used that equation to calculate predicted attendance based on the temperature, and then we calculated the error.